Hello friends, I welcome you in lecture number 30 on Laplace transform. In this lecture we will see how to find out inverse Laplace transform of this rational function. We have seen this type of problem in lecture number 29. This is similar to that problem. Here denominator is s raised to 4 plus 4 times a raised to 4. So we will first find out middle term for this, and then we will try to write down this term as a square of some another quantity. And we recall that formula for middle term is square of middle term equal to 4 times first term into last term. So we consider this s raised to 4 as first term and 4 times a raised to 4 as last term. So this is going to be 16 times s raised to 4 times a raised to 4, and this we can rewrite as square of 4 times s square a square. Therefore middle term is plus or minus 4 times s square times a square. So this we can rewrite as we add 4s square a square or 4a square s square, and we subtract 4a square s square. Now this first three terms can be written as square of s square plus 2a square, and this we can rewrite as square of 2as. Now using the formula of a square minus b square, this we can rewrite as s square plus 2a square plus 2as in the product s square plus 2a square minus 2as. So this is now product of two polynomials of second degree or two quadratic polynomials, and in the denominator we have s. So now we take the difference of these two. If we take difference of s square plus 2as plus 2a square and s square minus 2as plus 2a square, then this is going to be s square plus 2as plus 2a square minus s square plus 2as minus 2 times a square. S square will cancel out, 2a square will also get cancelled, and we have 2 times 2as, that is 4 times as. So this difference is 4 times a into s, and here we have s in the numerator, and that 4a we can set by multiplying by 4a and dividing by 4a. So now we are rewriting our function, which is s divided by s raised to 4 plus 4 times a raised to 4. First we divide by 4a and multiply by 4a. So here I write 4as, and this is product of these two quadratic factors, s square plus 2as plus 2a square, s square plus 2as plus 2a square times s square minus 2as plus 2a square. And now we replace 4as by difference of these two factors. We have seen that difference of these two quadratic factors is 4as. So we replace 4as by difference of these two quadratic factors. Here we write s square plus 2as plus 2a square times s square minus 2as plus 2a square, and this is equal to 1 divided by 4a. This I can rewrite as here s square plus 2as plus 2a square divided by this product. So we are left with s square minus 2as plus 2a square. Similarly here we will be left with s square plus 2as plus 2a square. So therefore we have s divided by s raised to 4 plus 4 times a raised to 4. This is equal to 1 divided by 4a. Now this is irreducible factor, and if you observe, if I split this 2a square as a square plus a square, then I will have s square minus 2as plus a square and plus a square, and this bracket is nothing but square of s minus a. Okay, we can check, this is s square minus 2as plus a square. So here last term should be a square, therefore I am writing 2a square as a square plus a square. Same thing I will do here. This I can rewrite as s square plus 2as plus a square, and here plus a square. Now this is equal to 1 divided by 4a. This we rewrite as square of s minus a plus a square, and this is square of s plus a plus a square, and we have ready-made formula for this. Therefore L inverse of s divided by s raised to 4 plus 4 times a raised to 4 equal to 1 divided by 4a. We have s minus a, therefore we multiply by e raised to at, and if we compare with 1 over s square plus a square, instead of s minus a, if we consider s, then we have 1 over s square plus a square, and inverse Laplace transform of this is sin at divided by a. Here we have s plus a, that is s minus minus a, therefore we have e raised to minus at and sin at divided by a. And now we can take this sin at by a common, and we will have e raised to at minus e raised to minus at times sin at divided by a. Now this I can rewrite as, I write 4 as 2 into 2, and I take 1 2 in the division of this into sin at. Okay. I combine this a, and I split 4 as 2 into 2. That 2 I am writing in the denominator of this, so that I can convert this in terms of hyperbolic function. This is nothing but sin hyperbolic at into sin at. So this is the required inverse Laplace transform of the function s divided by s raised to 4 plus 4 times a raised to 4. So we have obtained inverse Laplace transform of this function without using that partial fraction method. Okay. Otherwise, from this step we have to write this as as plus b divided by s square minus 2as plus 2a square, and same factor for this cs plus d divided by s square plus 2as plus 2a square. But here it is possible to write down this numerator as the difference of these two, and because of equal degree, both are polynomials of degree 2, we are able to write down 4as as the difference of these two, and we are easily able to convert this in terms of partial fractions. So whenever we have two polynomials of equal degree in the denominator, then we can try to check whether their difference can be set in the numerator or not. If it is possible, then we can go in this way, otherwise we have to use method of partial fractions. Okay, fine. So this is all about this session. I hope you like it. Thank you very much.